Good day, everyone. Today we are going to be considering energy quantization calculation. That is, we are going to be looking at past examination questions from this topic, energy quantization. And you will agree with me that this topic, energy quantization, have up to 3 or 4 subtopics, and we shall be considering at least one question under each of these subtopic. So the first part we are looking at is excitation energy, and we all know that electron in an atom, they occupy specific energy level, and when they gain sufficient energy, they may move from this energy level to higher energy level. That is when we say excitation occur. And the energy absorbed when they are moving from one energy level to higher energy level, we call it excitation energy. And the same way they are excited to higher energy level, they can as well lose the energy and come back to the previous energy level or to the ground state. And during these movements, electron either absorbs energy or emits energy. That is, when they are moving from a lower energy level to higher energy level, they absorb energy. And when they are coming back to the lower energy level, they emit energy in form of light. I will refer to that as photon. And that is what this first aspect is talking about. Okay. Now, if you look at the question here, the question says an electron drop from energy level minus 1.51 eV, that is electron volt, to minus 13.6 electron volt. So we have to calculate the energy of the photon radiated in joule, frequency and wavelength of the photon radiated. Okay, from this we can see that electron drops from this energy level to this energy level. As you can see, you will agree with me that this energy is higher than this. That is, electron is coming from higher energy level to lower energy level, and during this, definitely energy will be emitted in form of light, which is photon energy. And when this happens, the change in energy from the level it is coming from to where it is going to is given by this equation here, where E subscript I represents the energy level of where the electron is coming from, and E subscript F represents the energy level of where the electron is going to. Delta E simply represents the change in energy, that is the photon energy, the photons emitted during quantum jump. Okay, now following this through, we can see that this is our initial energy level where the electron is coming from, and this is our final energy level. To find the change in energy, that is the photon radiated, we substitute them into this formula, and that is what we have here. Okay, and that will give us a 12.09 electron volts. But from the question, we were asked to calculate the photon radiated in joule, but what we did here is photon radiated in electron volt. In one of our previous video, I told you that electron volt is another unit for energy, but we can easily convert this one to joule by doing what? By multiplying it by 1 electron volt value. In one of our previous video, we've come across this as well. You can see the constant even in this bracket. 1 electron volt is equal to 1 electron volt is equal to 1 times 10 raised to the power minus 19. So to take energy quantity or any energy value from electron volt to joule, you multiply by the value of 1 electron volt, which is 1.6 times 10 raised to the power minus 19, and that is what we did here to take the value of our energy to joule. And the value of the energy in joule is 1.934 times 10 raised to the power minus 18 joule. Okay, Now, going to the second question, we have to calculate the frequency and the wavelength of the photon radiated. Remember that when this photon energy is emitted, when this photon is emitted, the energy, the change in energy from the level where electron is coming from through where it's going to, is also equal to hf. This hf represents the energy of the photon emitted, that is the energy of the light emitted. And in this formula, h represents Planck constant, and whenever it is needed to be given, as you can see in the bracket here, yf here represents the frequency. And from the wave equation, this frequency is also equal to c over lambda. In this one, this c represents the speed of light, while the lambda represents the wavelength. Okay, let's quickly see how we can find our frequency and wavelength in second question. Okay, now you can see from what we have, we've calculated the energy in question 1, and that photon radiated, which is light energy, is equal to hf, as I've explained earlier. And making f the subject of the formula, it means the energy will be over h, and from there we can substitute the value of h. H is given as a constant in the question already. Okay, and substituting that value, that we are going to have f to be equal to the value of energy calculated in question 1 divided by h, and that will give us 2.93 times 10 raised to the power 15 hertz. And from this one, where our frequency equal to c over lambda, lambda represents the wavelength and c represents the speed of light, we assume that the electron is moving with the speed of light here, and the speed of light is given in question as this value here. You can see it here. Okay, making lambda the subject of the formula in this equation, we are going to have c over f, and that is what we have here. Okay, now making lambda the subject of the formula, we can easily say our c, which is 3 times 10 to the power 8, divided by our f calculated here. Just calculated our f now, so, and that will give us 1.02 times 10 raised to the power minus 7 meter as the value of our wavelength. And with that, we are done with question number 1, which has to do with excitation energy. That's first subtopic under energy quantization. Now the second subtopic we are going to be considering here is Einstein photoelectric equation. What is photoelectric? When light of sufficient frequency falls on a metal surface and electrons are emitted or ejected, that is that phenomenon is what we call the photoelectric effect. That is when light shines on the surface of the metal and the light is having a frequency that is sufficient enough to eject an electron from the surface of the metal. We will say photoelectric effect as occur. And Einstein came up with equation for this effect, and that equation is what is represented here. Okay, or you can as well write it as hf equal to E plus work function. Okay, what are the values of these parameters? E represents the kinetic energy of the electrons that is emitted from the surface of the metal excuse me, when light shines on the surface of the metal, while hf represents the energy of the incident photons, that is energy of the light that is shining on the metal. And work function is just like a barrier in the metal that we want to prevent electrons from being emitted from the metal. So which means this energy of the energy of the incident photons must overcome this work function before electron can be ejected from the metal. And when electron is ejected from the metal, it travels with this kinetic energy. That is what this equation is saying. Okay, now let's look at the question here. The question here says if the kinetic energy of the photoelectron, okay, if the kinetic of the photoelectron is 3.80 times 10 to the minus 16 eV, we have to calculate the frequency of the photon that ejects the electron from a metal of work function 3.5 times 10 to the power minus 16, and we have some constant given, Planck constant is given, and 1 electron volt is given in joule. Okay, very simple. From this question, we have our energy given as we have our energy, the kinetic energy of the electron given as 3.80 times 10 to the power minus 16, and we have our work function. Kinetic energy is E. We have our work function, which is W naught, given as this, and we have to find our frequency here. So to do that, in order to do that, let's substitute the value given in the question into this place. So this is our kinetic energy in place of E. We have our HF here, and we have our 3.5 times 10 to the power minus 16 in place of work function. So mathematically, we can collect the like times. So that is what makes HF to be equal to, that is this plus this. If you collect the like time, that is lifting this to the other side. That's lifting this to the other side of the equation. Okay, now, and adding this to this, it will give us 7.3 times 10 to the power minus 16. That's our HF, which means we can now convert our HF to joule by multiplying this value with 1 electron volt, and that is what we have here. Okay, and after doing that, we make our F the subject of the formula. Our H is already given here as a constant, so we make the entire value of this, we put it over the value of our Planck constant, which is H, and we have our frequency to be 0.176 hertz. 0.176 hertz, that's the frequency there. Okay, let's go to the next subtopic under this energy quantization. The next subtopic we are going to be considering. Okay, just before we do that, you can see that in this video we are only dealing with calculations, but there are so many other information attached to this. That is maybe the definition of excitation energy, ionization energy, definition of work function, threshold frequency, electron volt, and some other terms and some other explanation. And to have a very good knowledge of all this, you can just try and get a copy of Revamped Physics e-notes. We've been talking about this in all our videos, and this is a note that we designed for all the topics for O-level physics from grade 10 to 12, that is from SS1 to SS3. So if you have a copy of this note, it covers everything that you may need in being successful in any of your O-level examinations, such as WAEC, NECO, GCE, UTME, even Cambridge IGCSE. And to get this book, just type this website address into your browser, and it will take you straight to where the note is, or probably you can chat with this number on WhatsApp to get the note. And having a copy of this note gives you an access to at least a term-free online tutorial in physics and mathematics. That is at least 3 months free tutorial in physics and mathematics. We've been saying this for a very long time, and people have been benefiting from this. More than 500 students are already benefiting from this, so you can be part of them as well. Okay, now moving away from this, let's look at the next subtopic under this energy quantization. The next subtopic we are considering here is production of X-ray. Production of X-ray is very close to what is happening in photoelectric effect. You know, X-ray are produced when electrons are accelerated under high voltage. When electrons are accelerated under high voltage, and that happens when you make a light to shine on a metallic substance like such as filament in X-ray tube to liberate the electron from the filament, and these electrons are accelerated with very high voltage. That is when X-ray is produced. And from this example 3, we have we have a 500 kilovolt electricity, that is voltage, high voltage, which is applied, is supplied across a straight tube. We have to calculate the velocity of the electron produced in the tube. Okay, that's one thing we need to know here. We have our voltage, very high voltage, that bring about the acceleration of electron, given as 500 kilovolt, and that one is converted to 500,000 voltage. Now we are looking for uh, the velocity of the electron produced. Now, when these electrons are produced, there's something we call stopping potential. Stopping potential, and this is the voltage applied at the anode to stop the photo current. Now, what is photocurrent? That is the current that bring about the photoelectric effect at the anode. And this stopping potential is just the voltage that attempts to stop this photocurrent, and this uh, stopping potential, which is given here, is always equal to the kinetic energy of the emitted electron. That stopping potential is always equal to kinetic energy of the emitted electrons, okay, in that X-ray tube. And that is why we are equating them, that is EV equal to half mv square. Remember, kinetic energy is given by half mv square, and in this case the m here will be the mass of electron. That is why we use m subscript e in this formula here. So it's mass of electron. Okay, now let's bring out all the parameters here. We have a 500,000 voltage, and we are looking for the velocity of the electron. Please make no mistake here, try to see this very well. This V represents the voltage, capital letter V, while small letter v represent the velocity. So substituting the values that we have here, our E, electronic charge, is given as a constant here. You can see it, and that is 1.6 times 10 to the minus 19 coulomb. So, and our voltage is 500,000, and we equate that to half mv square, where our m represents the mass of the electron, and it is given as a constant in the equation as well. Making multiplying this side of the equation, we have this by multiplying that side of the equation, and also working on this aspect, we have this. I'm making phi squared the result of the formula. That makes us to have 8 times 10 to the minus 14 divided by 4.56 times 10 to the minus 31, and that will give us 1.75 times 10 to the power 17. And finding the square root of this value, and that is what we did here to have the value of our v, and our v will be equal to 4.19 times 10 raised to power 8 meter per seconds. Let's move to the last subtopic under this energy quantization. But before we solve this problem, I would like to quickly say this. If you've been part of this, you've been watching our video for a very long time, or you are just joining for the first time and you are yet to subscribe, please do subscribe to this channel and click on notification button, so that whenever we make a video like this, you get a notification. And if this video has added any value to you one way or the other, please let us know at the comment section and give us thumbs up. And if you also have any question, or you have any complaint, or you have any additional information that you want to pass across to us, please let us have them at the comment section. We really appreciate that. Okay, and like I said earlier, if you really need more information on all these topics, because in most of our videos we only treat calculations from past examination questions, but if you really want real information, the detailed information of all this topic that we've been treating, please get a copy of a Revan Physics e-note, you can check the description of this video on this channel. You see a link to that book there. Okay, the last example here, we are talking about the subtopic de Broglie wavelength. Now, de Broglie is the name of a scientist, a physicist to be precise, who proposed that electron as a particle could as well have a wave-like properties. That is, electron as well can behave like a wave, and that makes de Broglie to come up with this equation for the wavelength of the electron when electron behave like a wave. And what is in this equation? Lambda represents the wavelength, and that is equal to h, which is Planck constant, over mv. M here is mass of electron, while v is velocity or speed of the electron. That is what this one simply represents. Okay, let's go back to the question. The question says, calculate the wavelength of an electron of mass 9.1 times 10 raised to power minus 31 kilogram, moving with the velocity of 2 times 10 raised to power 6. That is, this is the mass of the electron that is moving with this velocity, and Planck constant is given, and we have to find what? The wavelength. Using this formula, which we also have here. Okay, we can just substitute all our values. So lambda will be equal to the value of h given in the question over the product of m and v. Okay, that is mass of the electron and velocity of the electron, and that will give us 3.63 multiplied by 10 raised to the power minus 10 meter. Also, we can as well calculate this wavelength using this equation. Remember, mv here represents the momentum, so which means we can as well derive another equation for this wavelength here, which is equal to square root of 2 E capital V M. Okay, in this one, this V here is not the speed. This V here is potential difference, that is the voltage. When the voltage is given instead of speed, we can make use of this. And this E here is a constant, is electronic charge, and will be given whenever it is needed. So instead of this, sometimes the parameter given in a question may make us to consider this formula, and this formula also represents de Broglie wavelength equation as well. Okay, and with this we come to the end of the calculation on energy quantization. And before I go to the practice exercise, I would like to advise us once again, please, if you are yet to subscribe to this channel, please do subscribe to this channel, because when you do that, it will make the channel to stay alive. And also remember to click the notification button, so that when any of our video is live, or when we're having a live session, you'll be notified. And for more information on all the topics we've treated so far in our videos and the subsequent ones, please, you can get a copy of Revan Physics e-note at a token. And getting a copy of that book will give you an access to 3 months free online tutorial in both physics and mathematics. And you are free to ask any question at any time from this note. Even after that 3 months, you are free to chat with the author on WhatsApp and ask any question in physics based on this on the information in the note, and even any other information in your textbook. Okay, now I will want us to practice these questions. We have our 2 practice exercises here. Please do practice this, and drop your answer at the comment section. And if you have any problem working around these questions, you can let us know at the comment section, and all your questions will be attended to. Thanks for watching.